Hi, my name is Oldridge, and I'm here to present our RecSys 2020 tutorial, Feature Engineering for Recommender Systems. This is a tutorial put together by myself, but mainly by my colleagues Chris Deotte and Benedikt Schifferer, who are going to be leading the breakout sessions. Those labs that you'll be doing are going to be an interesting exploration into the actual features, and we've got a number of different sort of techniques and methodologies that you can try out. So as I said, my name's Evan. I've been working in recommender systems for about 10 years. I'm now a senior manager at Nvidia, and I'm kind of building on a team that's building tools for recommender systems, trying to accelerate them on the GPU. My colleagues Benedikt is sort of has some experience in recommender systems and joined the team a little while ago as a deep learning engineer. And Chris Deotte is one of the KGMon team members from the competition or the RecSys competition as well. And he's been with Nvidia for almost a year now, and is part of the sort of the KGMon team. He's a 4 times Kaggle Grandmaster, and we're very excited to get a chance to learn directly from him, and I'm excited to share with you guys the workflow and the work that we're going to do. So the focus and the goals of this workshop are to improve model performance for RecSys and sort of learn some of the best practices for pre-processing and feature engineering, and then to figure out how we can optimize the experimentation pipeline. So really leveraging GPUs to accelerate this, iterate quickly, and make this feature engineering and pre-processing happen quickly. The techniques we're going to use are sort of both on GPU and then mechanisms for scaling to production level systems. So we'll cover sort of the basics of what the pre-processing ops are, and then talk about how to scale them and build them up. If you look at sort of a generic experimentation pipeline for RecSys, often you start with the data set and you're working through trying to figure out basically what are the features you should be including. So you do some pre-processing, you do some feature engineering, you feed it through a model, and you come up with a sort of a performance of that model, and then you often sort of end up in this iteration cycle where you're iterating over the feature engineering and pre-processing multiple times. And so when it comes down to the RecSys competitions and tabular data competitions, they're generally won by this feature engineering stage or this pre-processing stage, and the faster you can make that, the better off you are, the more important it is to make sure that phase is happening efficiently and quickly. If we look at the last 5 years of RecSys competitions, the majority were won using very simple like XGBoost or LGBM models. And there are some examples of CNNs and some simpler deep learning models as well in that context. But the majority of these papers cite their feature engineering as the sort of the main reason why they won the competition, and it makes a lot of sense here. Accelerating the pipelines is incredibly important. It allows you to do more and more experiments. So, we've shared the image on the right of the CPU versus GPU powered workflow, basically being able to iterate over the data faster and faster and be able to explore faster and faster. In the challenge in 2019, we showed how we could speed up the code 15x from the initial CPU code. In the RecSys 2020 challenge, we were 28 times faster than some optimized CPU code that was efficient at running on a significantly large cluster. So we'll walk you through some of the feature engineering techniques that we've done and how to scale them and make them faster on GPU. The overall outline of the tutorial is sort of this short introduction that I'm going to give into the features that we're going to explore, the recommendation models, and some of the high level. And then I'm going to hand it over to Chris, who's going to do some hands-on labs with the Jupyter notebooks, and he'll pass it on to Benedikt. And then I'm going to explain a little bit later on in the tutorial a bit about some of the techniques and tools like Dask and Dask cuDF and NVTabular that we're building these operators on top of. So as we dive in, I wanted to address sort of the deep learning aspect of this. In a lot of RecSys or a lot of domains, deep learning uses automatic feature extraction, and I think there are tools like TabNet or some other algorithms that are designed for doing automatic feature extraction in the tabular space, but they're really not mature, and you can see that just in the sense that the majority of the competitions and the majority of companies that I know are doing hand-tuned and handcrafted features to really try and produce powerful models. Develop the feature engineering step is a very important step, and that may change in the future, but for now it seems like a very important concept. So the feature engineering that we're going to cover, it really relies on the different types of data. So you're either dealing with categoricals are among the most common data. Sometimes you have unstructured lists. Numerics are quite common, so things like price or delivery time. Timestamps and time series are very common, and so we cover a few examples of those. In the recommender space, images, text, social graphs, geolocation can also be incredibly important. We don't cover that in this tutorial explicitly. I think there's other examples of that in the past. We're going to focus on the techniques in bold. So target encoding, count encoding, categorify, and combining categoricals. And then on the numerics, doing things like binning into categoricals, normalization, Gauss Rank techniques. And then looking at sort of the number of past events in a past time frame and a difference in time lag for time series events. So there's a limited amount of time we've had to focus here, but at a high level, these are some of the techniques that that we've used in the past when we're developing features for recommender systems. So at a high level, we're not trying to cover the whole recommender space, but it's important to kind of have a basic understanding of recommender models. There's a few ways you can frame a recommender problem. In this case, we're looking sort of more at a point-wise recommendation. And you could do that using tree-based models like CatBoost, XGBoost, or LightGBM. These are very common approaches in the RecSys challenges. You sort of split the data set by information gain per feature. And there's no normalization required because the split can happen kind of at any particular point in time. There's a few issues like XGBoost can't handle raw categorical features. You have to kind of turn it into either an ordered list or a one hot. On the deep learning side, there's a lot more feature engineering that needs to be done and a much bigger impact that feature engineering has. And so we'll see that as we sort of take a look at the notebooks and explore the feature engineering stages. What we're doing today is going to be diving into this very interesting data set that we found on Kaggle. It's the e-commerce behavior data from multi-category store. If you search for Kaggle, the RecSys 46 marketing platform is the originator of this. Essentially, what's available are view, add to cart, and purchase events for a sort of I think 6-month time frame. And basically, what we've turned this into is a sort of a positive target is the purchase events, and the negative target is the add to cart. So Chris is going to do a bunch of EDA to sort of get you familiar with the data set in the first session, and we can go through and do a deeper exploration there. But I wanted to sort of tease the data set and build the understanding. To give you an idea of where we're going with this, you can see sort of the XGBoost and deep learning models that we've developed. With and without feature engineering, you can see roughly a 6% improvement on the without feature or of the XGBoost type models, and a 13.4% improvement in the deep learning models. So it's these are sort of the preliminary results. In the live tutorial, we may find a bit more improvement or some other models that we explore. But at the time we're recording, this is what we have. So you can see it does play a significant role. A 13% improvement in your area under curve is quite a significant change in performance of the model, and it highlights just how much you can improve deep learning through feature engineering to get it to be close to on par with the XGBoost model. Some of the tools that are being used in the sort of the first part of the example, cuDF is our data frame library that the Rapids team has developed. It's essentially a library that does data frame operations on top of CUDA, and so it allows you to do GPU accelerated data frames. So there's sort of several libraries available. There's cuDF and Dask cuDF. Dask cuDF helps you scale. We'll talk a little bit more about Dask in the future, but if you're familiar with pandas and you've done feature engineering through that, you're going to be very familiar with the cuDF API because it mimics the pandas API for the most part. It's an amazing library, and the team there has done a really incredible job developing it. And it gets even more interesting with Dask cuDF. So it's a really exciting tool to learn and understand. There's sort of a C++ version of it, as well as a sort of a Python version that allows you to mimic the pandas directly. You can see, the C++ library, if that's the type of work you want to do. There's or the type of low-level work you want to do. You can kind of access the CUDA kernels almost directly and get a little bit of extra performance out of it. If you prefer Python, it's like I said, very much like pandas. In fact, in many examples workflows, you can just essentially replace import pandas with import cuDF as BD, and you can get a very similar functionality. And so you'll begin to see and get used to how this works inside the example notebooks. But you're going to be familiar with this if you're familiar with pandas, and if not, it's worth exploring and diving in. The accelerations are quite significant, as we'll see. In this case, we're looking at DGX performance, so running on a scaled cluster. And the speed ups over CPU and GPU are in the hundreds. Generally speaking, at a high level, what I've seen on the workflows that I've developed is at least a 10x improvement in performance for a similar cost kind of GPU relative to a CPU cluster. So you can see significant improvements in your workflows by operating on the GPU, and as we'll see, using Dask cuDF, you're not sort of bound to the size of the GPU memory in terms of your data set. So I'm going to turn things over to Chris here, and he's going to dive through some of the work in the hands-on lab, and I will return in a little bit to talk with you about the NVTabular library and some of the ways that we're kind of accelerating and scaling this across the GPU.
All right. Hello. We're now ready to begin the hands-on portion of our tutorial. My name is Chris Deotte. I'll be presenting the first half, and Benedikt will be presenting the second half. Let me introduce myself. I'm a senior data scientist at Nvidia, currently working on the RAPIDS framework. I graduated with a PhD in mathematics and computational science. For the past few years, I've been doing research in data science, and I've been actively participating in online data science competitions where I've recently earned the title Quadruple Grandmaster at Kaggle.com. Today, we will be working through a bunch of Jupyter notebooks. You can see the list of Jupyter notebooks on the left here. All the notebooks you see today can be downloaded from our GitHub repository. The link is here on the right. Also, if you download from the repository, you'll also have solutions to all the exercises we work on today. You'll also have code for downloading and preparing the data, and you'll have code which trains full models with and without feature engineering. Before we begin, I want to point out 3 important things about Jupyter notebooks. First, the code we'll be running today will be using a GPU. So you can double check that your machine has a GPU and it has sufficient memory by running the command !NVIDIA-SMI. Also, after each notebook, you'll want to close the notebook down, which will free all of the memory and get you ready for the next notebook. That command is in the bottom left of the slide here. And then if you want to continue working on a notebook, but you wish just to clear the memory and reset the data frame, you can run the command on the bottom right. Okay, let's get started. Today, we are going to learn about feature engineering and preprocessing to accomplish 3 goals. 1, improve model accuracy. 2, accelerate experimentation pipeline. And 3, scale our code to large production systems. The easiest way to accelerate feature engineering and preprocess is to execute your code on GPU instead of CPU. So today, we'll be doing our data framework using Rapid's cuDF, which is similar to Pandas API, but will be executed on the GPU. So we load Rapids with the command import cuDF, and we double check that we have a GPU accessible with the command NVIDIA SMI, and we see that today we have a Tesla T4 NVIDIA GPU, and we have 16 gigabytes of memory. All right, so for all of today's Jupyter notebooks, we'll be working with a real-life data set to demonstrate pre-processing and feature engineering. The data set is an e-commerce behavioral data set from an online marketing platform. The data shows, it has 3 events. It shows when a user views an item in an online store. It shows when a user adds an item to their cart and when a user purchases an item. And the data comes from the time window of October 2019 to April 2020. So we need to predict the target. So we're going to define a positive target when a user purchases an item, and a negative target is when a user adds an item to a cart but does not purchase in the same session. And we will split the data set as follows. The training data, we'll use the October 2019 through February 2020 as training data. We'll validate with the month of March 2020, and we'll test our model on April 2020. Let's have a look at the data set. So we load the data set here, and we notice that the training data has 11 million rows. The validation data has 2.5 million rows, and the test data has 2.5 million rows. Each has 19 columns, so it's a large data set. And we can take a glance at what it looks like here. So we have a bunch of categories, a bunch of features, a bunch of columns, and each row is one event on the online store. So for each event, we have a timestamp. We have which user was involved. We have which product was involved. We've got the price of the product, the brand of the product. We got information about which categories the product belongs to. And we can break the timestamp down into hour, minute, weekday, day, and month. So if we check our targets, we will notice that 30% of the targets have a value of 1. That's because 37% of the targets of the events are purchase, and 63% of the events are an item, a user puts something in their cart but does not purchase. Other facts, we've got a total, our data combined is 16.5 million rows. We've got 3 million unique users. We've got about 200,000 unique products, and we have 10 million unique sessions. So let's go ahead and take a glance at the data. So we'll notice that a bunch of the features are categorical. So the first question we want to know is the sparsity. So we would like, for categorical features such as product ID, we would like that a single product shows up multiple times in our data set. That way we can start to observe patterns. If a product only shows up once, well, we can't really detect a pattern. So we notice here that on the x-axis is all the products. So all the products that only show up once, we have 40,000 of them, and you can see, but we do have some product IDs that show up, 20 times or more. Similarly with user and brand, we have some that only appear once, but others appear more times. And then the category values, nothing appears once. So category values will appear, thousands of times in the data set. So this is good. This means we can find patterns with the category values that appear frequently, and we'll have to do something special to values that only appear once. let's go ahead and look at associations with the target. So in these plots, we can observe two things. So this plot here shows various product IDs that occur frequently. So this product ID occurs 300,000 times. And then it shows from this red line, you can see that particular product, how often it is purchased. So you notice that different products have a different purchase rate. So our model can learn that. And we notice same applies for other features. For instance, certain users. So some users don't purchase anything. But some users, every event they're involved in, it's a purchase. So once again, our model will learn about different users. And there's other trends we notice too. Take an example of this. So construction is the most frequent category 0. This value occurs 5 million times, and then medicine and stationary occur less frequently. But we notice that the red line decreases. So category values that occur less frequently, we notice that they have a less often is the target 1, and when a category value appears more frequently, the target is 1 more often. So these are things that we want our model to learn. We want a model to learn, to find patterns based on how frequently values occur. We want our model to learn patterns based on, which users purchase stuff and which users don't. And we'll be doing that today with things such as count encoding and things such as target encoding. And lastly, we can analyze the data by date. So on the x-axis here, we have date. On the y-axis, we have the average mean of purchasing for that particular date. And we see on certain dates, people don't purchase very often, and on other dates, they purchase a lot. So once again, we'll be able to create features using time, and our model can learn this. All right, so we saw how there's different patterns in the data, patterns that relate to frequency of occurrence, patterns that relate to which user or product we have. We see that there's patterns in time. So in today's tutorial, we're going to learn how to build features that allow our models to access these patterns. The last thing we do is we shut down our notebook, and let's begin feature engineering. We're now ready to begin feature engineering. So the first thing we do is we're going to go ahead and read in our data. But then we're going to run. So we execute the command train isNA_sum. So we notice that in our 19 columns, we notice a bunch of data is missing. So this is a common occurrence. Real world data is messy. So frequently, before we can begin feature engineering, we have to clean the data. And the most common thing to do is to check out all your columns and see if any data is missing. So we observe here that in the brand column, for example, 946,000 elements are missing. So we don't know the brand. Similarly, we're missing some user data, and we're missing some data on the categories. So before we can do any feature engineering, we're going to have to fill this missing data with something. So we notice that all of the missing data is actually in categorical features. So it'll be pretty easy for us to do. But first, let me demonstrate one of the problems of missing data. If we run this command here, we're going to group by brand, which we observed had missing data, and then we're going to calculate the mean and count. We notice that it doesn't actually calculate the mean and count for the missing data. So these are the brands that are not missing. So this command just ignores missing data. So similarly, when you try to build models, a lot of models treat missing data differently or can't handle missing data. So that's another reason that we're going to have to deal with it. So for categorical features, it's very easy. All we need to do is just add a new category called unknown and fill the missing data with unknown. It's also a good practice to make a new column where you basically have a flag to indicate whether you filled in missing data. Because, maybe later in the week when you open up your data set, you might, and you look at your new copy, you may forget which was the original data and what was the data that you filled. So here we're going to go ahead and do that. We're going to fill the missing categorical features with a new category value called unknown. And similarly, we're going to make a new column called NA, where we're going to put a flag indicating if we went ahead and filled it in. Let's go ahead and check. We checked, and we now notice there is no more missing data because we just filled it in. And if we execute this command earlier, where we group by brand and aggregate the mean and count, we now notice that the missing data is being included in the calculation. And we even notice the interesting thing that the brands that were missing have a very low mean, right? The proportion of unknown brands that actually get purchased is 30%, whereas the whole global average was 43%. All right, so it didn't happen in this case, but sometimes a numerical feature will have missing data. And a numerical feature we can't fill with the value unknown, we have to put a number there. So a common way to do that is to put in a mean or median, and you can either put in the mean or median of the entire column, or if the numerical feature is part of associated with different groups, you can do a mean and median per group. So for instance, let's go ahead and just randomly replace 1% of all prices with null, missing data. So we now see that 1% of the prices are missing. And we're just going to demonstrate how we could fill them in. So the way we'd fill them in is we actually going to look for each missing data from each missing price. We're going to see what category 2 that price is associated with, and we're going to replace the missing price with that category 2's median. So we go ahead and do that. We're grouping by the category 2, calculating the median, and similarly as before, it's a good practice to add an indicator column. So here we are, we're adding an indicator column. And let's go ahead and add it in. So there we have it. So originally, we artificially removed 1% of the prices, and then we just went ahead and filled them back with the average for the category 2. And once again, if we check the price, there are no missing values. So as we continue in future notebooks, we will use the original price. This was just sort of a demonstration of how we would deal with if price was missing. And as always, we're going to shut down the notebook at the end. Okay, we just finished pre-processing and filling the NANDs. So we're now ready to go ahead and engineer our first feature. So a very simple yet powerful and often overlooked technique is combining categories. So if you have two categorical features, so for example, let's say you have weekday and you have hour of day, you can combine these two columns and make a new column, which is weekdays hour of day. So for example, in your new column, you might have Saturday at 10 a.m. or Monday at 6 p.m. And it's often the case that the original columns by themselves did not have any patterns or strong associations with the target. However, when you combine them, it might be the case that Saturday at 10 a.m., there's a lot of purchase going on. So a high association with target equals 1. And maybe Monday after work at 6 p.m., there's a high association. And it turns out that many models like decision trees, if the original features don't have a strong association with target, then the decision tree cannot effectively split the data up and find patterns. So let's go ahead and observe this by making some artificial data. So we're going to randomly make some data here. So we randomly made 400 rows, and we made 4 features, F1, F2, F3, F4, and we have a target, a binary target. And let's go look at the association between these features and the targets. We notice that feature F1 is categorical. It takes on the values 0, 1, and 2. However, there's no association with target. When feature F1 takes on the value of 0, half the time target is 0, half the time target is 1. Similarly, when feature F1 takes on the value 1, half the time the target is 0, half the time the target is 1. So you see, feature F1 by itself has no power in predicting the target. Similarly, feature F2 by itself has no power predicting the target. However, let's see what happens when we combine feature F1 and F2. Now, feature F1 had 3 values, 0, 1, 2. Feature F2 had 2 values, 0, 1. When we combine them, the combination now has 6 values. So for example, we can see that the combination can be the case that F1 is 0 and F2 is 0. When that occurs, the target is 1 90% of the time. And when F1 is 0 and F2 is 1, the target is 1 10% of the time. So you see this new feature, which is the combination of F1 and F2, has a very strong association with the target. And that's what we will often see. So let's go ahead and build a simple decision tree with this artificial data and see how the tree does before and after the feature engineering. So here is the tree before feature engineering. So you can see here at the root node, it says value equals 200, 200. That means we have 200 negatives and 200 positive targets. After the first split, it doesn't have much information gain because look, this left node is 130 negatives, 147 positives, and the right node is 70 negatives, 53 positives. So you see, we didn't have much information gain. We didn't do very well at predicting when we have a positive and negative. Now let's go ahead and make a decision tree using our new engineered feature, F1 combined with F2. Wow. So immediately, we can see that the colors are more strong. So that indicates that we have more information gain and our nodes are more pure. So we notice after the first split, right here in the left child, we have 190 negative and 110 positive. So that was an information gain. In the right child, right node, we have 10 negative and 90 positive. So you can see it used this new feature, and based on the new feature, it was actually able to predict when we will see positives and when we will see negatives. So this is exciting. So you might say, well, wow, this is really powerful. Why don't we just take every categorical feature in our data set and combine them all together and just combine everything? So the problem with that is the cardinality. So if you combine all of the categories together, then in your new column, you'll have so many different values that each value will only contain very, very few observations. And with very, very few observations, we can't really generalize a pattern. If you see something occur, 2 or 3 times, we can't be confident that that will also occur in the unseen data. So for example, if we were to take all of our features in this artificial data, F1, F2, F3, F4, and just combine them all together, well, the new feature you can see here will have 10 unique values, and each one of these values only has a small number of observations. So that won't generalize as well. So the best practice is to combine categorical features that already begin with a low cardinality. That helps. Also, only maybe combine a few together. You can do some EDA and try to figure out, which ones, when combined together, have strong associations with the target. So EDA is one of the things you'll really need to do. And a little command that can help you to see what the cardinality is this command describe. and it'll make this little table and show you your different features on the top. And then it shows you how many unique values there are. So F1 has 3 unique values, F2 has 2 unique values, etc. So now it's your turn. I want you to go ahead and practice on our data set with the e-commerce. So we're going to go ahead and load in the e-commerce data set, if you recall, and it had all these different columns. And then I want you to practice, do some EDA, combining various columns and try to figure out which combinations will yield a new feature which has a strong association with the target. So that's for you to do. After you work on that, the solution is posted in the GitHub repository. Now let's discuss optimization. So there wasn't too much to optimize here. But I guess the one thing we could optimize is the EDA, the exploration of which columns are good to combine. But the actual act of combining columns is pretty quick already. So what we're going to do here is we're going to convert the data set. So now we have the data set in both pandas and cuDF. So pandas is executing on the CPU, and cuDF, which is rapids, is executing on the GPU. So one of the easiest ways to get a speed up, to optimize speed, is to move your code from the CPU to GPU. So you see here, when we try to analyze, so in this case, we just went ahead and we combined some of our columns and we looked at their different means and counts. And on the CPU, that took 3.6 seconds. And when we did the same thing on the GPU, it took 1.6 seconds. So approximately a 3-time speed up. Later in future tutorials, we're going to see much more drastic speed ups. But already we're observing that moving our operations to the GPU is a way for us to increase the speed of the work. Great. So we've now learned our first technique for feature engineering. Let's go shut this notebook down and look at our next technique. In our previous Jupyter notebook, we learned how to combine categorical variables, and feature engineer a new column, which is the combination. Now in this notebook, we're going to discuss a technique called categorify. This is the process of getting categorical variables ready for models, whether they be deep learning models or boosted tree models. So we're going to go ahead and load in our data set again. There it is. So the idea is this. A categorical variable takes on a whole bunch of different values, but those values might be strings, those values might be numbers, who knows how big. But what most models want is, or well, particularly if we're doing deep learning, where usually we'll feed a categorical value into an embedding layer. And what it wants is it wants integers starting from 0 to C, where C is the number of unique category values. So let's look at the product ID. So the product ID we have here down this column. This is a list of all the unique values. So we see that the values range in value from 1 million all the way up to 100 million, just big random integers. But then if we use this function called factorize, it'll actually go ahead and convert all those numbers into just the numbers from just the integers from 0 to 164,000. So you see, and also if we had done this to a category value called of the column called cat2, well, originally it had words like medicine or construction, and it would similarly turn those into integers. Another advantage of doing this factorize and turning into integers is it saves memory space. let's imagine that the original column had very large numbers or very large words, and we'll demonstrate that in an example. So, sometimes when you have user IDs, to keep the users anonymous, the column will have a whole bunch of hash values. So these are long strings, which take a lot of space. So let's go ahead and see how much space it would take if our data set contained hash values. So we went ahead and turned all the product IDs into their hash values. Now we have a whole column. And remember, this column is 11 million rows, and we have all of these long strings. So that's a lot of data in memory. And specifically, that is 1, 2, 3, 1, 2, 3. That's a 1 gigabyte of memory. Now let's go ahead and factorize that, which again is the process of turning it into very small integers, 0 to c, and let's see the size of those integers. So those integers are only 90 million. So we notice that by using the integers to represent the categorical feature instead of these long, hash values, it takes 9% of the original memory. So we've now seen two advantages. One advantage is getting the data ready for certain deep learning, certain models. And the second advantage was to use less memory. And a third advantage, what we can do when we categorify, is we can take any categorical value that appears very infrequently. We can just group them together. So let's say a particular user only appears once, and we have a bunch of users that only appear once. Well, we'll just rename all those users into a new category value called other. So let's go ahead and look at product IDs, and we notice that all of these products, so we're listing how many times each product ID occurs, and all of these product IDs down here, they only occur once. So what we can go ahead and do is all of this code here, we're going to take all of the product IDs that occur 5 times or less, and we're just going to put them into a new category. And when we're done with that, now, before we had 164,000, different values in our categorical feature product ID. That's the cardinality. And now, after we did this categorify and we put everything with 5 or less counts into its own group, we now only have 76,000. So you see, we've significantly reduced the cardinality. And this is good. This makes each value have more observations per value, which means any patterns that exist between this category feature and the target, it will generalize better to unseen data. So this helps all types of models. And there we went ahead and did it. So now it's your turn to practice this. So I want you to go ahead and I want you to categorify the category feature brand. I want you to apply a frequency threshold minimum of 20. I want you to map the low frequency categories to the ID 0 and map any unknown categories to the ID 1. So this is for you to do. Afterwards, you can view the solutions online in the GitHub repository. Now let's go look at optimization. So all of this code here, this was the code we used to categorify a column, and there's a bunch of different processing. So this will benefit a lot by speeding it up. So let's see how long it takes on CPU versus GPU. So we're going to go ahead and load it in. We're going to load it onto the CPU. While it's loading, I can just remind you of the advantages of categorify. So the advantages were it helps enable deep learning models to use the feature. It significantly reduced the size in memory, and it prevented overfitting by grouping categories with low frequency into one new category. Okay, so we now have converted our data set to pandas. So first we're going to see how long it takes to categorify the column user ID using CPU. So we're waiting. So there, it took 21 seconds to convert that column. And now let's see how long it takes on the GPU using cuDF Rapids. Wow, it was instantaneous. So it took less than half a second. So it was 21 seconds using pandas on the CPU and less than half a second using cuDF on the GPU. So we had a speed increase somewhere around 45 times. That's really huge. So we see how when we categorify our categorical variables, you see the advantage. We're gonna want to do that on the GPU with Rapids. All right, so let's go ahead and shut down this notebook and get ready for our next feature engineering technique. Target encoding is my favorite feature engineering technique. So categorical variables are tricky sometimes to input into certain models like boosted trees or deep learning. So for boosted trees, some boosted trees can't handle categorical variables. So you'll need to one-hot encode them or do some other transformation. And with deep learning, you'll need to put them through an embedding layer or also one-hot encode. So at the end of the day, the model wants to learn about that category and what the different values mean. And target encoding is a really neat feature engineering technique, which allows us to extract the information from a category variable and put it right into any model we want. So let's see how that's done. So first, we're going to go ahead and load the data. There's our data. All right, so this is how it works. Let's consider the categorical feature brand. So brand has 4,600 different values. And if we input this feature into any of our models, we want our model to learn about the significance of brand. Well, we could ask ourselves the question, given a brand name, so for instance, given the brand name Zuru, what's the probability that somebody purchases this brand? And the probability is 28.5%. What about the brand Amega? So the brand Amega is purchased 34%. So what we have here is we for each brand, we found all the rows that had that brand and then calculated the mean of the target. We did that with this group by operation. So once we do this for all 4,600 brands, we can merge this back onto our data set. So now each row has a new column called target encoding of brand. So look at this first row here. So the first row, the brand was unknown, and an unknown brand has the probability of being purchased at 30%. So we add that new feature. And then down here in this row, for the brand Apple, it has a probability of 42%. You see, so for each row, we added this new column where we target encoded the mean. And we could do this, we could do multiple columns at once. So for example, instead of just doing brand, we could actually combine brand with this column cat2 and then calculate the mean of these combinations. So for instance, whenever we have, the combination of brand Zilling and cat2 being the product a kettle, well, this combination, nobody ever buys. The target is 0. So, we can do combining categories and target encoding at the same time with that command. And you do the same kind of merge. You just merge it on. Here's this new column where we target encoded brand and cat2 and added it onto our data set. So as we mentioned earlier, target encoding is a really powerful technique. It works with any model because in the end, we have a new column, which is just now a numerical feature, and all models can handle a numerical feature. And we've extracted, a lot of the essential information from that categorical feature, which contains all the patterns. So it makes it very easy for any model to learn. It's a very, very powerful technique. So what we just showed you was just basic target encoding, but we have to be careful because it can easily overfit. So we want to do something called smoothing. So let's explain what smoothing is. So when we target encoded the category brand, we noticed that some brand names showed up very infrequently. For instance, the brand name Zilling, it only showed up twice. So there isn't much pattern there. And likewise, some columns, some brands even only show up once. So we have many brands here. This bar right here, this tall bar, it has the X value of 1. So 350 brand names only show up once. So if that one time it shows up, it's purchased, we don't want to say that that brand name is 100% purchased. So we need to be very careful when a brand name shows up infrequently, not to take that pattern as fact. And the way we do that is with smoothing. So smoothing, what smoothing is defined in these 2 bullet points. If the number of observations for a particular value within a category is high, then it's safe to use the mean of that category value. But if the number of observations for a particular value in a category is low, then we don't want to use that. And instead, we just use the global mean of the entire column. So the way we do that is with this formula here. And this formula uses a smoothing parameter. And if we let the smoothing parameter be a large number, like say 1,000,000, then we would use the global mean always. And if the smoothing is 0, then we would always be using the mean. And when we pick a smoothing parameter in between, then it starts to, use the global mean when it should and use the other mean when it should. All right, so now it's your turn. So we want you to go ahead and target encode the feature brand together with category 2 and use a smoothing of 20. And you'll do it based on this formula here. So go ahead and try that on your own. To see the solution, you can download the Jupyter Notebook from the GitHub repository. All right, so let's see the effect of smoothing. Let's see how it helps. So here we go. We're going to go ahead and so now we're going to go ahead and do some smoothing. So to do smoothing, we need both now the mean and the count value, and then we're going to use that. We're also going to need the global mean, and then we apply our formula here. So we use the count, we use the mean, we apply the formula. Here we're going to use a smoothing of 20, and we're going to go ahead and calculate the error. So let's look at the error. So here is the error. Let's look at these 2 errors. So the top error is target encoding without smoothing. And we notice that when the count is low, so when in this left column, this is within a particular value. If a value only shows up 1 time or 2 times or 3 times, a very infrequent within a thing, we see that the error was large, 43% error, 48% error, 41% error. But when we applied the smoothing of 20, now look at the error. For the values that were small, we're not having such a large error. So we notice that using smoothing, it decreased the error, which is to be expected because without smoothing, we don't expect the pattern to really transfer when the value occurs infrequently. And we can also notice this with the ROC AUC score. So once again, if we just target encode without smoothing, then and just use that single encoding as a prediction on our validation set. So we target encode with the training data, and then we use that value and we merge it onto the validation data and compare those predictions with a true target of the validation error. we get a ROC AUC score of 57% when we don't smooth, and we get a ROC AUC score of 58% when we do smooth. So once again, we see how smoothing truly helps us capture the pattern and then use that pattern to predict unseen validation data. All right, so there's even another thing you can do to improve target encoding even more, and it's called out of fold. So you can target encode with k-fold. And the way it works is this. So first, let's point out that how did we just use target encoding to predict the validation set? So the way we did it is we used a training data set. We calculated all of the target means from the training data set, and then we used those means and concatenated it to the test data set. So notice that the target encoding that we concatenated to the test data set, well, it came from computation using the training data set. So you see the new column, it didn't actually use the test data set, it used a different data. So likewise, you can do the same thing with the training data set. You can break the training data set into 5 folds. So just, break it into 5 20% subsets. And then when we want to go ahead and add the new column to say fold 5, so we want to add this new target encoding column to 20% of the training data set, the fold 5. Well, we don't use fold 5 when we make the calculation. So we only use the data from fold 1 to 4. We use the other 80% of the data. We calculate the means from that 80%, and then we concatenate. We merge that onto this fold 5 20%. And similarly, when we want to calculate target encoding for fold 4, we use folds 1, 2, 3, and 5, et cetera, et cetera. So that mimics the idea that we don't actually use the data itself to calculate its own target encoding. And here is some code to do that. So we wrote a function here. It does target encoding. You can choose the number of folds. So you'll use 5 fold. You'll choose a smoothing of 20. And we can just go ahead and apply it. And it's computing. So there we go. So in this case, it actually... It did target encoding. It concatenated these 4 columns. It used smoothing of 20. It used folds of 5. And it calculated the target encoding. And so it made a new column here on the training data set. And this first row right here. So to calculate this value, 0.30 in the first row. So remember, the first row might have been part of fold 0. So it actually didn't use that data. It used the other 80% of the data. It calculated the mean from that, and then it went ahead and merged it onto this. And then it went ahead and merged and then it put on the target encoding onto the validation set by doing all of the train at once. So to summarize, we saw how target encoding is a very powerful feature engineering technique. It extracts the essential information of a categorical feature, and it lets it be utilized in any model, whether it be boosted trees or deep learning, lets it be used very easily. We saw how just by itself, it's very easy to overfit. So to prevent overfitting and to make it generalize more, we want to add smoothing, and we also want to add k-fold target encoding. Let's take a look at how to optimize this. So we're going to go ahead and load in the data. And so we loaded in the data, and we're going to compare how to optimize it. So as we've discussed before, the easiest way to speed up code is to run it on the GPU. So if we do target encoding using pandas, so first let's run it on the GPU. So if we use Rapids with cuDF and we run it on the GPU, then this function, which does all the 5 folds and the smoothing, it takes 7.5 seconds. And I'm not going to run it right now on the pandas on the CPU. You can do that at home, but if you do it, it'll take 70 seconds. So it's about 75. So it's 10 times slower. So we notice a 10-time speed increase, and we would sort of expect a bunch because, as you saw, it's very computationally intensive. There's you have to do the different 5 folds. You have to group by, calculate a lot of means. So we see a 10 times speed up. Wonderful. So that summarizes target encoding. So let's go on to learn our next feature engineering technique, count encoding. Go ahead and close our notebook. Now we will learn about count encoding. Let's go ahead and load in our data set. As always, we're going to pre-process and fill the nands of the categorical features with a value called unknown. Here's our data set. So here's the idea. When you have a categorical feature, the values like product ID, for instance, the values inside, some values occur only a few times, and some values occur a lot of times. So if you just give this column to a model on its own, most models can't learn on its own whether something is rare or popular. So what we're going to do is we're going to make a new column where we're going to tell it how often each value appears. So for example, if we run value counts, in this left column here, these are product IDs, and the right is how frequent, how many times they appear in our data set. So for instance, this first product ID appears 300,000 times. So it's very, very popular. Whereas this product ID down here only appears once. So it's very rare. So the way we give this information to our model is we've just merged this column onto our data set. So we go ahead and do that. And then what we notice is we've added a new column. And in this new column, so for every row, so here's this row, here's this product ID, and then this new column says that product ID appears 881 times. So now the model will actually know each product ID and whether it's occurs rare or whether it's popular. And this has many advantages. We can also combine categories. We mentioned this before. So in this example here, we're actually going to combine the 2 columns, cat2 and brand, and then we're going to count that combination. And you could see it here. So for instance, the combination when cat2 is a winch together with brand 2D, that occurs in the data set 31 times. And we just go ahead and merge that on. So count encoding accomplishes many things. So one is it teaches our model about whether something's rare or popular, but it also allows the model to see patterns that previously didn't exist. Let me give you 2 examples. If a product ID only showed up once, well, that product ID by itself has no predictive power because there's no pattern there. Something only happened one time. But now, if you group all of the product IDs together that had a count 1, now they're all called count 1 product IDs. So now the model can learn what's special about product IDs that appear once, what's special about product IDs that appear 10 times, 100 times. So now it'll actually treat the products. It'll actually be able to find patterns amongst the rare products and the popular products. Now I'll point out, when you count encode the trained data set, there's multiple ways to count encode the validation and test data set. If you have all the data sets in front of you, you can just count encode each one independently. But to be more true to a real life situation, you can count encode the trained data set, And then that new column you create, you just merge it on both your validation and your test data set. All right, so now it's your turn. So go ahead and use count encoding and go ahead and count encode the column user ID. To see the solution, you can see the Jupyter notebook in our GitHub repository. Let's now talk about optimization, about speeding this up. So this is a data frame operation. So if we want to speed it up, instead of doing it on the CPU in pandas, we can do it on the GPU. So let's go ahead and do that and observe what kind of speed up we get. So first, we're loaded in the data set again. And now we'll go ahead and run it on the CPU. So it's running on the CPU. And there it took 10 seconds. Now we're going to go ahead and run on the GPU. It took half a second. Wow. So it's 20 times faster. So once again, we demonstrate. So we just learned about count encoding. And then furthermore, when we implement it, we're going to want to do that on the GPU using Rapids. And we've noticed here we can get it can go 20 times faster. All right. Let's go ahead and close down this notebook and learn about our next technique.
Hi, I'm Benedikt, data scientist at Nvidia in the recommendation system team. Previously, I worked in e-commerce in Germany where I built the in-house recommender system for them. And prior to Nvidia, I graduated from the Columbia University in New York with a master in data science. I will continue this tutorial with the labs for normalization and time series. So we go to binning. So first we load our data. And what is binning? Binning maps multiple categorical or numerical features into group. And the reason we want to do this is it prevents overfitting because it groups similar values together. Or we can add some expert knowledge to the model because we know that some values or some categories should be together. A really simple case is a binary flag where we say like, oh yeah, the numeric feature is greater than 1 or it's 0. Other examples are we want to bin weekdays into the work week and weekend, or hours into morning, afternoon, late afternoon, evening, or night. Or we can bin an age into child, adult, or retired. So we can look in our data and we can see that we have like a different behavior, like the hours between 0 and 3, they're like lower, and that's probably because it's night and people are less active. So to create a binning, we will create a separate data frame, which creates a mapping from the original value to our bins. So in this example, we have our hours from 0 to 24. And the first 4 hours are binned with 0. The next 4 hours are binned to the 1. Then we have 7 hours binned to the second, to the third value 2. And then 6 for 3, and then the last 3 hours as 4. So if we look in our binning table, that's like our mapping. And then we just merge it based on the hour to our original data frame. If you now look at the probability of the purchase probability per bin, we have exactly like the different behavior where we can see a peak in the second bin, which is probably the most active one, or really late at night, maybe late night shoppers. So binning reduces the cardinality of unique values, and therefore a model can easier learn the relationship to the target variable. Another reason we want to apply binning is to standardize numeric values per category. For example, in our data set, we have the products or product categories and price information. And for example, we know that we can probably buy pretty good headphones between $100 and $200. But for a smartphone, we probably have to pay more, and good smartphones are probably in the price range from $400 to $1,200. So to make it the model easier, we want to have like a standardized way that low, like cheap headphones look similar than cheap smartphones. And a way to do that is by binning. If you look at the distribution, you can see that the distribution for headphones is a little bit lower or left than for smartphones. And we can see the same if we look at the mean price or median price per category. So for headphones, it's the mean price of 316, but for smartphones, 456. So yeah, they have like a different price distribution. So we want to do the binning for the category level 0, 1, 2. So we group them together into a combined category. And we want to calculate the price bins based on the quantiles. So we look at the quantiles 10, 25, 0.25, 0.5, 0.75, and 0.9. And then we iterate over it, and we calculate this quantiles for each category, and then merge it back to our trained data set. So our trained data set has now additional columns, which are like the price boundaries to define if a product is in the first bin or in the next bin. Yeah. And now we need to create the mapping or like or write the price bins based on these boundaries. So first we define our column price bin and assign a default value of -1 because that doesn't exist. Then we iterate over our list of percentiles. And in the first case, we have no lower boundary. So everything which is smaller than our first price boundary is assigned with I, which is in that case 0. And for each additional price boundary, you say, okay, it has to be bigger than the previous one. And at the same time, it has to be smaller than the current one to assign it to the next bin I. Finally, all values which are bigger than our highest price boundary, which is like the 0.9 percentile, is assigned to the last bin. So we can execute it. And then we can look at the example for the price bin 3, where you can see like the price is $7.61. This is between the price 0.5 of $7.60 and price boundary of percentile 0.75, which is 11.58. And you can see that like in the last columns, it's the same case, that they're always below that. So we create a lot of dummy variables for the boundaries, which we don't need, so we can drop them. And then we can look if our price bins are beneficial or helpful. So we group them by price bin, and we can see that the lowest price bin of 0 over all categories has a smaller target probability of 0.33. And like the price bins between of 3 and 4, they have a high probability of 0.37. So we see that this feature can be helpful to predict our target. And yeah, because probably the smallest bin are like just cheaper products, and the last bin is maybe a little bit too expensive. That's the reason it drops again. So practice, as in all in our tutorial, we have some exercises for you. You should look at the column TS weekday and look for a good mapping, how you can map weekdays together. We provide the solutions in our folder solutions, and this exercise is for you. Now we look at the last step about optimization. So right now, cuDF has no native function for binning per group, but cuDF will always add new features to it, and this will maybe be implemented soon. So stay tuned for the latest update. Yeah, but we can improve our implementation. So right now we calculate our price boundaries and map it to the data frame, and then we do the mapping. But that requires more memory. Actually, we only need the information from the current price boundary in the previous one. So we can add in our for loop to drop the values or columns we don't need anymore. So let's continue. We restart our kernel to free memory. We load our data again. We combine our categories again, that we look at the category 1, 2, 3 together. This is our group function. group binding function with the additional line that we drop previous values we don't need anymore. This is the pandas version. This takes over 2 minutes to execute. That's the reason I will skip it here. And here we apply the group binding function to our cuDF data frame. So you can see it's calculating step by step. And this is done in only 6 seconds in comparison to 130 seconds. If you look in our data frame, we can see we have our final column with our price bands. In our experiments, we achieved even a speed up to 28.2 times. Yeah, and we can shut down our kernel for free memory. So this was the notebook about binning. It helps to prevent overfitting the model. We can add some expert knowledge because we know how to group values together. And we can normalize certain numerical variables per category. So we continue our tutorial with normalization for numerical input features. So first we load our data, and our data has only price as a numerical feature. That's the reason we use some techniques from the previous notebooks to generate more numerical features that we can analyze more. One is target encoding. And the other one is count encoding. And then with both, we have like more numerical features to analyze. So what's normalization? Normalization is required for neural networks to leverage numerical features. Tree-based models, they do not require normalization because they do like a split on the numerical features. And based on the split, it's partitioned the data into 2 different leaves with different statistics. But yeah, and this split is independent of the scale of the features. But our neural networks learn or are trained with backpropagation. And the error or like the gradients are backpropagated. And if your input features have different scales, the one with a larger scale is the updates and the parameters are updated more in the beginning. So for example, we have our price features, which is between 0 and 10,000. And we have like target encoding, which is between 0 and 1. And price will contribute in the beginning more to the final prediction because it's all the parameters are randomly initialized, and that's the reason price will contribute more, and that's the reason we'll get more updates. So we have a visualization from Jeremy Jordan, how the updates will look like based on 2 features. And on the left side with different scale, you can see that the updates are more alternating. And that's the reason it finds the sweet spot slower and not optimal. But if they're both normalized to between 0 and 1, the updates are more smooth and it finds the spot directly in the middle. There's like different normalization techniques which we will discuss. Like we have normalization with mean and standard deviation, we have a log-based normalization, you have the scale to 0 and 1. Then we have a Gauss Rank as a next notebook and the power transformation, which we will not discuss as for a limit of the time. So normalization with mean and standard deviation. It's the most common approach, mainly known from statistics classes. So we subtract the mean and divide it by the standard deviation. And our output is normalized with a 0 mean and a variance of 1. So if we do that, it's pretty simple. Just subtract the mean and the standard deviation. If you look at the histograms, we can see that now our scales before is between 0 and 300,000, and now it's between minus 0.5 and 3.5. It's still not normal distributed, but the scales is definitely much closer to a normal distribution. That's the reason we look at the next one. The next normalization techniques is a log-based normalization. So some input features, as our previous one, has like a long tail distribution or a school distribution with like a lot of values in the beginning and only a few with a large range. So what we can do is we apply first the logarithm, and then we calculate, and then we subtract the mean on the log transformed values and the standard deviation divided by the standard deviation. And then we have like a normal distribution between with 0 mean and variance of 1. So we do that for our count encoding for the product IDs. We apply the log and we add +1 that if there's like 0 values, that this is not getting minus infinity. It's not defined. Then we divide it. If we now look at our distribution, we see the original distribution, and now our output distribution is still not fully scale normal distributed, but it's in the right range between -2.5 and 1.5, with most values maybe between -0.5 and 1. So this is definitely much closer to a normal distribution, and then a neural network can learn better. Our third technique is to normalize it between to scale it between 0 and 1, our feature. In our experience, this works great with target encoding values, like values which are like maybe a percentage or like already between the scale between 0 and 1, but they're like more like between 0.5 and 0.6 maybe. So we want to scale it. How does it work? We calculate the min and the max of our feature, and then we subtract the min and divide it by the range, which we can calculate by max minus min. So we get the target encoding. We use target encoding category 2, and we can plot our output. And you can see that our values are going up to 1, and it's going up to the lowest one is 0.0. We cannot really see the values as there's only a few. I have some the most values in the middle. Yeah, for normalizing features for neural network, the best practice is to try to have a normal distribution. Having that said, we experience that the scale to 0 to 1 can sometimes be beneficial as well. And it's in the end some practice and or like just some tests to try out a different normalization for feature groups to see which gets the best performance. So as in all notebooks, we have some practice as well. So it's your turn. You should normalize the feature's price, target encoding for weekdays, our category 2 brand, and count encoding for category 2. And plot the raw input features and the different normalization techniques we showed you in this notebook, and then describe which normalization technique seems to be the best in terms of it looks normal distribution. We have the solution in our solution folder if you want to take a look. We skipped the optimization in this notebook as the calculations are pretty simple and they're super easy to do with cuDF or pandas. Okay, so we continue our normalization of numerical features, and now we will introduce Gauss Rank. So first we load our data again, and we use some techniques to add more numerical features. And yeah, in the previous notebooks, we discussed why we do normalization. We learned some basic strategies for normalization. And in this notebook, we provide normalization techniques, which is called Gauss Rank. So Gauss Rank is a transformation which transforms any arbitrary distribution to like a Gaussian normal distribution. And how it does it, it's compute the rank. It scales then the values from -1 to +1, and then it applies the error-in function, which is the inverse error function. And you can see here the image from the left side, you have like this kind of random distribution, and the output is this really nice Gaussian normal distribution. So we will import some libraries for this, and we provide here a CPU and GPU version. And here we can go to the CPU version, which looks equivalent to the GPU one. It's like, yeah, we apply twice arcsort. So we know like, okay, in which orders our values are. Then we scale it to -1 and +1 linearly. We clip them, so the -1 and +1 are excluded from the boundaries, so we have to subtract a really small epsilon from the last value, and then we can apply this inverse arrow function. And now we can look at our count encoding for product ID. We have on the left side the input histogram. On the right side, you can see this really nice, beautiful normal distribution. So this is like a technique which is more used recently, like in, for example, Kaggle competitions, when there's like deep learning networks involved, as it's normalized the input feature pretty well. There may be one disadvantage we want to mention is because you rank the data twice and then you scale them linearly between -1 and 1, you kind of lose the information how big is the difference between 2 or 3 neighbors. So for example, if you have 3 values, 1, 1,000 and 1,001, they look pretty similar close after a Gauss rank, or could be. So you lose maybe the information how much they are like apart from each other. But yeah, as I mentioned in the last notebook, in the end we have to try out the different normalization functions and see which of them performs better for our data. So practice. Here we have an exercise for you too. And this time you should normalize the same features as in our previous notebook with Gauss Rank. So use price, the target encoding for weekday, hour, category 2, and brand, and the count encoding for category 2. And you should plot the non-normalized values and the normalized values with Gauss Rank next to each other. Then the optimization part. So we can see we can load our values once to CPU and GPU. We can apply Gauss rank on CPU. This takes like 3.8 seconds. And if we do Gauss rank on GPU, we like with 300 milliseconds. And some of our experiments, you got a speed of 80 times vector. This is something like 15 times maybe, but that's still pretty good. So we shut down our kernel to free the memory, and we will continue. So we will continue our tutorial and come to the next group of feature types. So we are looking at time series features. The first feature engineering technique is historical events. So for illustrating this type, we generate some synthetic data, which is just smaller and easier to understand. And we can scale it later to our original data frame. So we create a data set with like an item ID, then a user ID, an action, which could be purchased, like, followed. And then we create a timestamp, and we load this to cuDF. And yeah, in many real-world recommendations, probably in all of them, our information is collected in time. So the system logs normally like the events, what happened, like if a user seen a product, or like add to cart, or purchased, or maybe reviewed. And each of this log event normally has a timestamp. So like tree-based and deep learning models, as the data is tabular data, it's hard for them to make connections to other rows. It always looks at one row at a time. So we can help or improve these models by looking at relationship between different rows, or like aggregate data from previous rows in time history to the current row, because it's still like valid. It's something we could imagine. So like, oh yeah, how often was this product sold in the last 7 days? And it's just like we're looking in our log events over the last 7 days and count how often it was sold. And this information helps to define if this product is maybe popular, and that's the reason it will be purchased again. So we can look in our example, we look at the item ID with 1,000,001. And you can see that it was like purchased 1, 2, 3, 4, 5, 6, 7 times on the 1st of January, and maybe this information would help on the 2nd of January to predict if this should be recommended. So what you can do is we can extract this kind of history information for maybe the last 3 days or last 7 days or even last month or 3 months. So we can do like the sum of actions, or we can calculate the average probability that this action would happen. And in general, these kind of functions are called windowing function, and we use the rolling function in pandas or cuDF. And it looks on a preset window before the current row, and then aggregates the value. So first we have currently we have a data set based on item ID and user ID, but we're only interested in the item ID. So what we're doing is we group by item ID and timestamp and count and sum our actions. So sorting, we have an aggregated window function for item ID and timestamp. And we set the index as timestamp. This is important for the rolling function. So we can then decide how big our window is based on days, for example. And we don't have to be careful if there's like double dates in it or maybe a date missing. It will automatically understand how big it has to be the window. So we can apply this. We say like an offset of 3 days. So we have to add the D for days that the function knows what to do. And we say like, oh, we want to group by item ID and roll for 3 days. And then we want to do the sum. And afterwards, we drop the item ID as this is like not necessary. We can see that we have like a double index, item ID, and a timestamp. And there we have like our rolling window, and we can compare it. So for the 2nd of January, we have a count of 15. And we can see it's the 2nd of January and the 1st of January together. And for the 4th of January, we have 8. That's the reason we have like 2, 1, and 5. So that's 8 together. And it stopped ignoring the 1st because our window functions only 3 days. Yeah, but if we just apply the rolling function, we see it uses the current date. So for example, for the 4th, we looked at it, looks at the 4th, the 3rd, and the 2nd of January. But this would introduce some data leakage because we use the actually values of the 4th of January, although we don't have them. So what you have to do is we have to shift our data. And we use here just the shift function and shift it like by 1 day. And we override the values to 0 if the item ID is not equal anymore, because the shift is not by group by, it's just by shifting in general, which makes it pretty fast. And if we now look in our data, we can see that the 1st of January is empty because we haven't had values there. The same for the next item ID, as we have missed the data. And you can see that the 2nd of January is actually the values from the 1st of January, and the 3rd of January is actually the values of the 2nd of January, and so on. So now we don't have data leakage anymore. Finally, we have to merge our data back to our original data. And now we have here our full data set containing the historical information for our item ID. We can easily apply this for 7 days just by changing the offset. And this will be perfectly working for a different time windowing function. So practice, reloading now our dataset from our e-commerce dataset where we apply on. We create a date column because the timestamp includes hours and minutes. That makes it easier. And now you should calculate the number of purchases of an item of the previous 7 days. We provide the solutions as for all of our notebooks if you need some help to look into it. So finally, we want to compare the CPU and the GPU version. So this is our rolling window function. I will not execute the pandas version as it takes 42 seconds. But if we look in our cuDF version, it only takes 700 milliseconds. And this is a huge speed up. In our experiments, we got like up to 372 speed up. And this shows like how we can optimize our feature engineering with GPUs. We shut down our kernel to free up the GPU memory again, and we'll continue with the next time series features. We continue the tutorial with the next feature for time series, its differences. So first, we will generate some synthetic data again, like in the previous notebook. With the difference, we add now a price column to it. And the theory is we want to use the timestamp information in our data set to compare current values with previous values based on the history. And for example, we can look at the price. So we can compare the price current right now with the price maybe from yesterday per item or the price 1 week for the item and see if there's a differences. And if the price decreases, we can see there's maybe a promotion or in general, it's a smaller price. And that maybe boosts the sales for our product. So if you look at our synthetic data set, we have it similar than in our previous notebook with the additional price column. And again, like tree-based or deep learning-based models, they have difficulties to create these relationships from the current row to previous rows. And if we generate for them the feature, they are kind of guided and can look if these patterns can be used for predicting the target value, which just makes it easier and faster to train these models. So how we calculate the differences in price. So first we group our data by item ID and timestamp and take the mean per price as like the price should be constant per day, but maybe the price change was during the day. So we just take the average, but we need to aggregate it that we have only one price per item ID and day. Then we shift our data based on the offset. Right now we use the offset of 1. And if the item ID is not, we shift the item ID as well by the same offset. And if they are not equal, then we have to set the mean to none or like non-existing, because then there was no previous values for this item ID, like it's the first entry. And then we want to calculate the difference. So we have the current mean minus the mean plus the offset, also offset of 1. And if we look at our data, we can see this was the price mean, the third column, is the price mean current, then the price mean with an offset, and then the differences. And for example, on the 3rd of January, we can see the previous price, where it was 100. The current price is 125, and the difference is 25. So it was a price increase. The same for the 5th of January. The previous price from the 4th was 125. The current price is 110. So the difference is minus 15, and we can see now a price reduction. So finally, we have to rename the column and drop the unnecessary column. So we have only the price differences, and then we join it back to our original data and have everything together. So we can calculate this kind of differences, not only for the previous day, but maybe the previous week or the previous month or 3 months ago. Or we can combine them with other feature engineering techniques, like actually the historical event. And we can calculate the differences between how many products did we sold yesterday and how many products were sold a week ago, 2 weeks ago, a month ago, 3 months ago. And based on these differences, we can see trends if like a product maybe gets more popular or less popular. and can see patterns in the data. So practice, in this notebook, we have a practice as well. We load the original e-commerce data set we're using in this tutorial. We transform the date, that the timestamp to date, that it only contains day, month, and year, and no hour or minute. And you should do the calculation to create the difference between the current price per item and the previous price per item, so like the day before. If you need help or support, there's like the solutions file where you can take a look on it. So finally, we want to compare the CPU and GPU version again. So we create a function for it, which works exactly like in our introduction here. We can then convert it to a pandas data frame and execute the difference function that would take 14 seconds on CPU. And if we run the cuDF GPU version, we can see like 431 milliseconds. So this is like a speed of at least 28 times. In our experiments, we saw speed ups up to 43 times with the same code. Yeah, we finished the notebook for the time differences. We will shut down the kernel to free some GPU memory, and we'll continue with our tutorial.
Welcome back. So now we're going to talk about how you can take some of the operators that Benedikt and Chris have been sharing and scale them to production scale workload. So, how do you deal with this type of workflow when the data set you want to operate on is, is a terabyte, 5 terabytes, 100 terabytes, a petabyte. And so we have tools and techniques for dealing with this, some of which are sort of designed to allow you to scale and some of which are designed to make the workflow easier itself. So, the initial example we saw, and the EDA was done in pandas, you can see there's sort of limited limitations there in terms of CPU and system memory, and also, the speed and performance, the single-threaded nature of pandas that you can run. Rapids allows you to accelerate that using cuDF, and sort of there's limitations there with GPU memory. But the beautiful thing that the team has done is integrated with Dask. So just like pandas, you can scale pandas with Dask. You can scale cuDF with Dask as well, and it allows you to basically iterate over partitions of the data in chunks. So there's sort of a schedule that gets created of the operations that need to happen. And that schedule allows you to sort of iterate over larger chunks of data using lazy execution and just sort of optimizing and scaling to system memory and GPU memory. The tool that my team's developed, NVTabular, sits kind of on top of that Dask cuDF library. So we're leveraging all of the hard work that the Rapids team has done to basically build a tool that sits on top of that, that allows you to basically to describe what you want to do at the sort of at the operator level instead of the data frame level. So for example, if you want to normalize your data, instead of having to go through all of the steps required to normalize the data, so calculating the mean, calculating the standard deviation, subtracting, dividing, and then adding that column to the data frame and doing that for all of the columns in the data frame. Instead, we sort of created a structure around, specifying these are my categorical variables and I want to process them in this way. These are my continuous variables and I want to process them in this way. And you just specify, for the sets of variables, what types of operators you want to do. And under the hood, we create the Dask cuDF operations and the Dask graph and run that on the GPUs and scale it that way. As I mentioned, Dask is sort of a task-based library for parallel scheduling and execution. Super powerful. It allows you to iterate on data frames much larger, and even on a single GPU or a single system, it's often faster to break up the problem into chunks that you can operate on using Dask. So it basically takes the tasks required and schedules and executes them in an optimized task graph. And so we leverage that Dask cuDF in our underlying NVTabular library. NVTabular is our recommender system ETL on GPU. So it's basically a way of kind of encapsulating a lot of these feature transforms that that we've been describing here, trying to come up with common feature transforms, and using Dask cuDF, we scale to unlimited data set size with that higher level abstraction. We also have batch data loaders for PyTorch and TensorFlow and hugeCTR, which is our sort of partner training framework in Merlin. So if you want to scale beyond to multiple GPUs worth of embeddings, hugeCTR is definitely a very powerful library and something to check out. And the Merlin kind of suite in general, if you search for NVIDIA Merlin, you'll find a lot about those different tools. But the data loaders themselves, so when you're dealing with a tabular data, there's actually a major benefit to working with these data loaders specifically. And if you go to our GitHub page, you can kind of see examples of the kinds of speed ups you can get as you sort of leverage the NVTabular pipeline to generate the data set. You can also leverage the data loaders to accelerate the training, often by up to an order of magnitude. So. And then the final thing that we're working on within that context is, we understand how hard it is to get to production. And so there's this challenge of taking data that's been transformed during training and performing those same transforms during inference. So what we do is we kind of package up the data transforms and in the NVTabular side of things, so that you can reuse them and apply them online, even during the training cycle and also online at inference time. So this is sort of our high-level view of what the ecosystem of recommender systems looks like. So you can imagine, in the top left, you've got a data lake where you're pulling your data, and NVTabular is meant to do these feature engineering and pre-processing steps, as well as the data loading into the model. And then, like I said, we've got this extra pre-proc config. The other part of our Merlin pipeline is Triton, which is our online inference server. We're looking at functionality and capabilities in other inference servers as well, but Triton is our focus to try and do feature engineering at inference time online. So, we talked about some of the accelerations here, and I just want to give you a sense of the speed up. This is from the RecSys challenge. So in this case, we used Rapids, a cuDF plus Dask, and then GPU accelerated XGBoost for training, a technology called UCX for transferring the data back and forth between. And we were able to accelerate from a single GPU or single CPU system in pandas down for 11 hours down to 2 minutes on a small GPU cluster of 4 GPUs. So it's 2 minutes begins to get to the cycle where you're actually you're in the workflow, you're making changes, you're coming up with new features, you're making progress. And that's how we won the RecSys challenge, really, was by iterating quickly on the data sets and coming up with more and more features and coming to those features very, very quickly so we could explore them deeply. And so that's sort of some of the techniques that we want to share with you here, and why we're working on this is allowing you to scale to GPU, and to scale to multiple GPUs easily means that that you can really quickly iterate over your data and large data sets. So it's just a high level of what the NVTabular code looks like. We're going to dive into an example that Benedikt's created for the ops that you've been working on and learning in terms of the feature engineering that you've been doing. But this is at a high level. This is what NVTabular does: is sort of specifies the categorical and continuous variables so that so the system underlying knows which operators to apply to which, and then specifies the data sets, your training and your validation data, and then the operators that you want to perform on that data, and then sort of the differences between how you want to treat the training and validation set. So doing things like shuffling the training set and applying the statistics there, or calculating statistics using the training set and then applying those statistics to the validation set. So there's a bunch of different techniques wrapped up in this, but you can see we've got 10, 12 lines of code here. The same code base so this is reconstructing some code that we found in the LRM repo, which is Facebook's sort of deep learning recommender model. Their ETL pipeline was roughly 1,200 lines of code. You could shorten it to about 500, but you could do it in 10 to 20 lines of code in NVTabular, and that's the high level ideas. We want to reduce not only the speed and the allow you to scale automatically, but also make these sort of pipelines much simpler to write by allowing you to just write what you want to do to the data instead of having to specify at a data frame level how you're going to do it. So now Benedikt's going to dive into a demo of the scaling here, and we'll see how the operators that you've worked on are kind of are scaled using NVTabular.
After Ivan gave you an introduction about the concept of Dask, cuDF, and NVTabular, I want to give you a hands-on introduction for these tools for scaling to production systems. We start with the introduction to Dask and Dask cuDF, which are under the hood of NVTabular. The material for the Dask and Dask cuDF example are based on the tutorials for the GitHub tutorial here, a YouTube tutorial, and another GitHub tutorial by Richard Zamora. Other useful links is like the Dask webpage and the GitHub tutorial from Dask itself. What is Dask? Dask is an open source library designed to natively scale Python code. In a longer answer, Dask is a library to parallel scheduling and execution. It can use to do the task scheduling and implement some optimization to customize workflows. And users can interact with Dask and the Dask collection API. The most popular are like the Dask data frame, which is kind of the version of pandas. We can replace it with Dask cuDF later, Dask array, which is similar to NumPy, and Dask back. How does a Dask data frame looks like? It's a convenient API to partition the data frames into chunks and execute the calculations per each chunk. So if you look at an example, our full data frames are like from January 2016 to May 2016, for example, and this is the full data frame. And then each chunk is a pandas data frame, or could be a cuDF data frame. So Dask uses DAG, this is like directed acyclic graph. So to use Dask, what we do is we define the data frame and it gets the schema. And then we define a lot of different operators and calculations. These are all lazy executed. That means they're just registered. And then until we actually say Dask, it should execute the calculation and the task. Then it will do the optimization on the graph and process the data with this optimized graph. So it can rearrange the operation and make them more efficient. This is like an example diagram. So you have like a collection, which could be a Dask array, a data frame, and so on. Then you have your graph itself. And then the scheduler defines then or if it's on a single machine or if it's on a distributed machine, and which worker execute which tasks. So the components of the Dask ecosystem is like Dask as the core library. Then we have like Dask cuDF, which is like the wrapper for a Dask data frame using cuDF. And distributed is like the library to distribute it over multiple nodes, so like multiple workers. And then we have Dask cuDA as using GPUs. The hands-on tutorial. So we first start to load our libraries, and then we have to initialize a client. There we can say like how many workers we want to have and how many threads per workers, what's the memory limit and the IP. We use here the local host. If you want to have more clients and like a master, you have to set up and configure it to use like multiple nodes. And this is now initialized. And the first thing is we read our data with the Dask data frame. Here, notice it takes only 50 milliseconds because it's only loading enough information to get the schema out of it. So if you look at the object itself, you can see it has all the columns in it and what's the type of the columns, but it doesn't load the data in memory. And then it splits them into partitions, and we can define how many partitions, and this makes it easy to distribute it over multiple ones. We can call .meta to get actually the metadata itself. And now we do like a simplified example, which is like the target encoding in a simplified version. So we combine two columns, category 2 and brand. We target encode the new column, category and brand. We merge them back on the training and validation set. And then we replace low frequent categories with the global mean. So that looks exactly similar than the pandas API. We can combine them here. We do a group by and calculate the statistic count and mean. We rename the columns. We merge them back to train and validation. We calculate the global mean. And the one thing, it's a little bit different in the API if we want to replace a value based on a filter. Here we have to use the where statement, and it replaces the value if the condition is false. So everything which is true, it stays, and the false one is replaced with global mean. You can see this takes only 50 milliseconds, because it's executed lazy. So nothing is right now calculated, it's just registering the tasks. And if we call then compute, it actually computes the calculation. We will not run that because it takes like 3 minutes just to execute it. But then we see exactly like we have the column with category 2 and brand, we have the target encoding count and then target encoding mean. And then we can close our client or finish the calculation. An important note to mention, or a comment to mention, is the difference between compute and persist. Compute is the command to execute the full graph and then convert it to a single pandas data frame in one node. And that's the reason we can show it here. In comparison, persist would generate all tasks, or like execute all tasks, but it still keeps it distributed because it's kind of just persisting it. And that's the reason it's actually not always great to use compute on a large data set, because if it's all getting like collected on one node, it could be bigger as the memory. And therefore, it's better to use persist. But if we use persist, you could not display our final output result here. Let's go and use Dask cuDF and do the same calculation on GPUs. So we take a look on our GPU, and it has 0 memory used so far. We import Dask cuDF and local cuDF client. So we initialize our local cuDF client, and here we define the memory pool size of 16 GB of our GPU. And here we can see it reserves already 500 megabytes just for basic information. We can load our data. This is lazy again. And here we do the same calculation as above with exactly the same syntax. It registering all the tasks. And if we now call compute, it will execute all execute our tasks. And this should be done in 14 seconds. Let's take a short time. Yeah, in 14 seconds. And we have the same data frame structure with a brand, TE count, and TE mean. You can use this to, you can use Dask cuDF to scale it over multiple GPUs on one single machine. So if you have like 4 or 8 GPUs in it, it would distribute them over the multiple GPUs, and you get a higher speed up and you have more memory available. You can see that it still has the data in memory, and we can close our client. So that's a short introduction into Dask and Dask cuDF, which we use in NVTabular. We are now at our final notebook. It's about scaling to production system with NVTabular. This notebook is an introduction to NVTabular with an example workflow for our e-commerce dataset to train XGBoost classifier at the end. NVTabular is an Nvidia library for pre-processing and feature engineering datasets for recommendation models. And it's particular that in industry, datasets for recommendation systems can increase to like terabytes or petabytes. And there are like certain challenges with operating on these large datasets. And NVTabular supports and makes them more easier. So the first challenge is like the huge data set itself, which can be up to terabyte scale. Then we have complex data pre-processing and feature engineering pipelines. So NVTabular provides operators on best practices to do the pre-processing and feature engineering. A bottleneck is the data loading. If the data loading feeding the data to the GPU is not efficient, the GPU is not fully utilized. So NVTabular provides some data loader. And with this pipeline fully optimized, it's the data scientists and research scientists can do repetitive experimentation and can try out much more experiments. So the workflow of NVTabular looks like you have in the beginning a data warehouse or data lake and do an export with a query to a CSV or Parquet file. Then NVTabular can do the feature engineering like filtering, imputing, binning, breakdown, combining features, can do pre-processing like normalization or count encoding or categorify, and then the data loading, like loading the data and provide it to deep learning frameworks like TensorFlow, PyTorch, or Nvidia's huge CTR. We provide some resources for NVTabular, like our GitHub link, then the GTC 2020 keynote announcement. There was a special session during the GTC 2020 for NVTabular, and our NVIDIA dev blog post announcement, and more example workflows. So NVTabular has four main components. First is the dataset, which contains the file names for training and validation and reads them in chunk if necessary. Then the operator, which defines a specific calculation, which could be, for example, count encoding, target encoding, binning, normalization. Then a workflow, which kind of organizes the full pipeline, which defines context, it registers all the operator, it optimizes the order of the operator, and collects some statistics, and finally saves them all to disk. And finally, our data loader, which provides the tabular data to PyTorch, TensorFlow, or Nvidia's huge CTR. Let's look at the example for doing the pre-processing and feature engineering for our e-commerce dataset and train an XGBoost classifier. First, we import our library NVTabular and the operator. Then we define our training dataset and validation dataset. Here we can provide a list of files if they're split over multiple files. In our example, we have only a single file for each. And then we use a NVTabular dataset and initialize it with the paths and define the type. We're using Parquet files right now. And here you can see like the full path name. Then we need to define our workflow. In our workflow, we have to initialize them with the data schema. So what are the categorical column names? These are like product ID, brand, user ID, and so on. Our continuous features as price, and we use timestamp. And label name is like our output or prediction we want to do, which is called for us target. Then we use the function add feature to define our workflow. Here we chain all the operators together as we provide them as a list. Now, our first operator is the lambda op, which is a nice op which gives a lot of flexibility. it takes as an input a customized function, which is applied to a column level for the data frame. So in our example, we use the lambda op for combining categories from our previous notebooks. And in this example, we want to combine the user ID with the product ID, brand, TS hour, and TS minute. And the lambda op will iterate over this list of columns, convert each column to a string, and concatenate them with the user ID as a string. Our next lambda op is we want to combine user ID and brand with TS hour, TS weekday, category 0, 1, and 2. So it's exactly looks similar, except if we have now here 2 columns in the end, user ID and brand. And then we want to categorify them. So as an input columns is the list of all columns we want to categorify. This is from the first combined categories. This is from the second combined categories. And then finally, all categorical columns in the default. And then we apply a frequency threshold of 15. That means all unique categories which has lower observation than 15 are mapped to a special category. Then we combine product ID with brand, user ID in category 0. And then do a joint group by. The joint group by is in this example a count encoding. So joint group by calculates statistic per group and then maps them back to the data frame. As default, it's used only the count. And as we use count, we don't have to define any count names. Like we don't have to say like which continuous variable it should use because it just do a count. And then it replaces the original columns with it. And finally, we do target encoding. So we do target encoding for brand, user ID, product ID, category 2, and the combination of TS weekday and TS day. And we encode the target column. So we do the mean for the target column, for brand, user ID, and so on. We use a 5-fold strategy and use a smoothing value of 20. Finally, we clean up previous photos and then apply our workflow to the train data set. And then we apply our workflow to the validation data set with the output path, output NVTabular train and output NVTabular valid. Note that we use here record statistic false, which means it uses the statistic from the train data set and apply it to validation set. For example, for target encoding or count encoding, it used the statistic from the train. So as a summary, we added following data operation, combine categories, categorify, count encoding, target encoding. NVTabular supports much more data operators like join to external data source or normalization strategies or fill in missing values. However, NVTabular is still in development and we will add new features and more operation continuously. After we saved our data to disk, we will restart our notebook and we will add 2 more feature engineering techniques which we learned in this tutorial. So NVTabular saves them in separate files. So we load all files for the train and all files for the test validation, and then concatenate them into train and valid. So what we add now is the group by bin feature engineering and some rolling window feature engineering. So we combine the category levels 0, 1, and 2 into one combined feature and then apply binning to it. Afterwards, we applied target encoding to the price bins. Then for the window function, we have to convert the timestamp into a date, which has no minute or hour. We want to do the window function for product ID and user ID. It means how often did the user viewed or maybe even purchased this product previously. So it's not data leakage itself because we don't use the actual information of today, but we look in all previous days. So probably if you are interested in a smartphone, you will look at the smartphone multiple times in history before you really make the decision to buy it. We drop unnecessary columns. we apply the rolling window function, and then save our final datasets to disk as train feature engineering and validation feature engineering. So we restart the notebook to free some GPU memory again. We import cuDF and load our datasets. Then we see our columns. And then we define the features we want to use for our XGBoost model. The XGBoost parameters here to note that we use the GPU version of XGBoost. And then finally, we just train our XGBoost model, getting to a validation AOC of 0.64599, which is, I think, pretty great. So this is the end of our last hands-on notebook. Coming to the slides. We provide additional resources here. So as already mentioned before, we have like the keynote for Nvidia Merlin for recommender system, which includes NVTabular. Then our product page. We have our dev blog announcement of Nvidia Merlin with our NVTabular dev blog. Then the specialized session for NVTabular on the GTC and our GitHub link. This is the end of our tutorial. I hope you learned the best practices for transforming tabular data, pre-processing them, adding more features, and do that in an optimized way that your pipeline is end-to-end efficient. And if that's pretty fast, you can do more experimentation, you can try out more features, and improve your model accuracy.